You live on a planet that is about 4.54 billion years old, and almost none of that time has anything to do with you. For most of that history, there were no trees, no animals on land, no eyes, no brains, just simple cells in the oceans, slowly changing. Complex animals only show up in roughly the last 500 million years. Dinosaurs ruled for over 150 million years. Your entire written history, the part with cities and empires and wars and movies, is on the order of a few thousand years. On Earth's full timeline, that is a rounding error. If you disappeared today, the planet's story would barely need to adjust. So here's the problem. If our entire high-tech phase fits into that tiny slice and the rocks do not preserve every detail, how confident are you that nothing similar ever happened before? Not Atlantis a few thousand years ago, but a truly ancient industrial phase, tens or hundreds of millions of years back, before mammals took over, maybe even before dinosaurs. We do not have written records from those times. We only have rocks, fossils, and chemistry. If something like us rose and fell that long ago, what would you actually expect to see today? That question is known in science circles as a Silurian-style thought experiment. You drop all the mythology and you ask one clean question. If an industrial civilization had existed deep in Earth's past, what durable fingerprints would it leave in the geological record? Not stories, not ruins still standing, but hard signals in rock that do not go away easily. You are forced to think less about buildings and more about materials, less about culture and more about physics and chemistry. Look at your own world through that lens. Think of power plants, cars, plastic packaging, landfills, mines, fertilizer, and the total burn of coal, oil, and gas. Almost all of it is temporary at the surface. Buildings collapse, metals rust, plastics crumble, but some things do not just vanish, they move into long-term storage. Carbon from fossil fuels ends up in the air, and the oceans, and eventually in sediments. Nitrogen from fertilizers changes the chemistry of soils and coastal waters. Plastics break down into microplastics and settle into mud. Long-lived radioactive isotopes end up locked into minerals. Those are the kinds of things that can make it into rock layers and stay there. From a geologist's point of view, civilization is not defined by skyscrapers or highways. It is defined by global disturbances. The rock record mainly notices events that change the whole planet at once, or at least leave synchronized signals in many different places. When geologists talk about major events, they point to patterns like sudden shifts in carbon isotopes, a thin layer full of rare elements, a spike in extinction, a global ash bed, or a sharp change in sediment type. If industry is big enough, it becomes one of those events. Civilization in that framework would show up as a thin slice where the chemistry and fossils look wrong compared to what came before and after. So what would count as proof if you were looking for an earlier round of industry? You wouldn't expect a fossilized city with intact streets. You would expect to see a layer where across many parts of the world, carbon isotopes suddenly change in a way that suggests huge fossil carbon release. You would expect weird patterns in nitrogen isotopes that hint at artificial fertilizer. You might see a strange mix of metals or traces of synthetic compounds that nature doesn't usually make. You might see a bump in extinction rates or a reshaped ecosystem right at the same level. One layer, many signals, same date. But here comes the first major clue that should make you uneasy. Most of the land surface on Earth is geologically young. Mountains rise and erode, rivers cut valleys and dump sediment, glaciers scrape landscapes clean. Volcanic activity covers older surfaces with fresh lava. Even if you do nothing, the combination of erosion and tectonics constantly refreshes the face of the planet. On many continents, the rocks at the surface are only tens of millions of years old, sometimes less, even though the crust itself is much older. Now, consider the oceans. They're worse for long-term memory. New seafloor forms at mid-ocean ridges, where hot mantle material rises and creates fresh basalt. That new crust spreads outward on both sides, carrying sediments, fossils, and any possible artifacts with it. Eventually, at a subduction zone, that same crust dives back into the mantle and melts. When you look at the age map of the seafloor, you see something striking. Almost all of it is younger than about 200 million years, which is less than 5% of Earth's age. There's no truly ancient seafloor left at the surface. So if a past industrial phase mostly used the oceans for energy, transport, and dumping, most of its direct material footprint on the seafloor would now be gone, remelted, mixed, and turned into different rocks. The ocean basins are not long-term archives. They're high-turnover storage, constantly reset by the planet's internal heat. You might say, fine, plates move and seafloor recycles, but what about the continents themselves, the parts that do not get subductive so easily? Can ruins just sit there and wait to be found much later? This is where erosion steps in. Erosion is not dramatic most of the time. It is slow, but it is relentless, and it is driven by simple physics. Rain falls, water runs downhill, rivers cut into rock and soil, picking up grains and carrying them toward lower ground. Wind blasts exposed surfaces. Ice in cold regions scrapes and grinds. Over thousands of years, even strong materials start to break. Over millions of years, entire landscapes are reshaped. Apply that to a city. Leave a city alone for 10,000 years and vegetation and weather will destroy roofs, walls, and roads. Leave it for 1,000,000 years and most of the recognizable structures will be rubble, buried, or washed away. On 10 million year timescales, the rubble is broken into sand, silt, and clay, moved by rivers, deposited in layers, maybe compacted into sedimentary rock. What is left in the record is not a city, it's a slightly unusual mix of grains and chemistry inside a rock bed, and even that is only where conditions let sediments pile up instead of being removed. But suppose some of that material does get buried, protected from direct erosion. Does that guarantee its details survive? No, because then you run into metamorphism, the process where heat and pressure literally rewrite rocks. When layers are buried deep or when mountain belts form and crush older rocks, temperatures and pressures climb. Minerals become unstable, atoms rearrange, and new minerals form. Fine layering can be smeared, folded, or erased. For example, simple limestone can turn into marble. Mudstone can turn into slate or schist. The original textures and structures can be lost. The rock keeps its general chemistry, but the fine-scale story is overwritten. Now think about what that means for any ruins caught inside. Concrete, bricks, steel, glass, all of that has specific structures and shapes. Under metamorphic conditions, the materials would recrystallize, mix with surrounding minerals, and lose their engineered textures. You would no longer see a wall or a beam. You would see a metamorphic rock with certain elements in it. Maybe a bit unusual, but no longer clearly artificial. Just as erosion grinds structure down from the top, metamorphism crushes it from below. Put all of these processes together and ask a direct question. Across hundreds of millions of years, what has a realistic chance of surviving in a way that still stands out as industrial, not natural? The answer is not buildings, it is not machines, it's global chemistry. Things that spread through air and water, that settle into sediments in many places at once, that change the ratios of common elements and isotopes across the whole planet. Those are the signals that stand a chance. This is why scientists talk about things like carbon isotope shifts from fossil fuel burning, nitrogen isotope changes from fertilizer, long-lived radioactives from nuclear activity, and stubborn synthetic molecules and plastics that resist breaking down completely. These do not rely on a single site being preserved. They imprint themselves into many layers in different basins on different continents. And even if most of the crust is recycled, some fraction of those layers can survive as evidence. So the real rule is blunt. In deep time, geology keeps the big global signals and throws away almost all of the local details. If an earlier industrial civilization existed, the only seriously robust way to detect it now is to look for a weird, sudden, global-wide chemical fingerprint, not to hunt for fossil skyscrapers. Buildings and artifacts are noise. Global chemistry is signal. That leads straight to the next step. If chemistry is the only reliable memory, you need a method to read tiny changes in thin layers and line them up across the world. You need a way to say, here, right here, something huge happened to the whole planet at once. That's exactly what geologists already do when they study mass extinctions and past climate shocks. And it's how you would design a real search for an ancient tech spike in Earth's rocks. How do you read a planet's past when most of its surface has been shredded or buried, and you only get a few scraps left behind? This is where geologists switch from looking at single rocks to looking at layers. And once you see how that works, you understand why any real evidence for a civilization has to show up as a specific kind of signal in those layers. Start with the basic rule. Layers equal time, but only in the right places. You don't get a perfect year-by-year record everywhere. You get it where material keeps falling and settling without big interruptions, like mud at the bottom of deep ocean basins, fine sediment in long-lived lakes, or snow in polar ice sheets. In those settings, new material gets added on top. Older material stays below, and over long periods, the stack turns into rock or compacted ice. That vertical stack is a stratigraphic sequence, and reading it is stratigraphy. In a clean sequence, the rule is simple. Deeper usually means older, shallower means younger, but you always have to check for breaks. Each layer is like a snapshot of conditions when it formed. Grain size, color, fossil content, mineral types, all of those details are data. If the environment is stable for a long time, the layers look similar. If something major hits the planet, the layers change sharply. That's the core trick. You're looking for spots where the pattern suddenly shifts. So what makes a boundary obvious? What tells you, right here, something big happened? There are a few classic signals. One is an ash layer, a thin band of volcanic ash spread over a region by a major eruption. Another is a sudden jump in isotopes, like a change in the ratio of light to heavy carbon in carbonates and organic matter, or a change in sulfur or oxygen isotopes. Those shifts usually mean the global cycles of those elements were disturbed fast. You can also see mass die-offs in the fossil record, where diverse fossil assemblages suddenly collapse to a few hardy species. Magnetic reversals show up too, as flips in the direction of magnetic minerals and rocks, marking times when Earth's magnetic field reversed. When geologists find a boundary that has several of these features together in many locations, they treat it as an event line. A well-known example is the boundary at the end of the Cretaceous, when non-bird dinosaurs disappeared. In many places around the world, that boundary is a thin, clay-rich layer with a spike in iridium and shocked minerals, plus signs of stress. You can trace that line across continents and in marine sediments. That's what a global catastrophe looks like in the rock record. Thin, sharp, and strange compared to the layers above and below. Here's the key point. Big events don't need thick layers to leave hard evidence. A band about 1/25th of an inch thick, 1 millimeter, can represent a few years of chaos that change the direction of life. If that band has a chemical fingerprint that doesn't match normal processes, and you find the same fingerprint at the same relative time in widely separated places, you know the planet went through something out of the ordinary. That's what you're really hunting. Planet-wide weird, unusual layers with synchronized timing. Geologists formalize this by picking golden spikes, official reference points in specific sections of rock. A golden spike is a location where a boundary is clear, maybe because sedimentation was continuous, fossils are well preserved, and chemical signals are sharp. They mark that spot as the standard for the base of a new time unit, then correlate other sections to that point by matching fossils and chemistry. You end up with a global time framework built on a chain of distinctive events. But this neat picture hides a big problem called missing time. Erosion and non-deposition can remove or skip parts of the record. When rock layers are eroded and then new sediments are laid on top, you get an unconformity, a gap. To the eye, it might look like one layer sits cleanly on another, but there can be millions of years missing at that contact. In some places, entire eras are gone, stripped off before newer sediments arrived. That means our rock archive has holes, sometimes huge ones, and they're not always obvious just from standing on the outcrop. Missing time matters for the civilization question. If you had an industrial phase that lasted a few 100,000 years, and it happened during an interval that is now represented by an unconformity in many important sections, you might have almost no record of it at the surface today. The sediments that recorded it might have been eroded away or never deposited in the first place. That does not mean the civilization definitely existed, but it means you cannot rely on a casual, "we do not see it, so it was not there" argument. You have to work with the parts of the archive that actually survived. This is where the strategy tightens. If industry leaves a spike, for us or for anyone before us, it has to be global, distinctive, and datable, or it gets lost in noise or gaps. Global because you need to see the signal in many places, not just one basin that might later be destroyed. Distinctive because natural processes can also change carbon, nitrogen, and metal distributions, so the pattern has to look wrong for known volcanic, biological, or impact events. Datable because to call something a civilization layer, you need to lock down when it happened and how long it lasted, using radioactive decay clocks, fossil ranges, or known reversals in Earth's magnetic field. So here's the blunt filter. If an earlier industrial civilization never altered the planet enough to create a clear global anomaly in multiple element cycles, it would be nearly impossible to prove it existed using rocks alone. If it did alter the planet that much, then in principle, a targeted search in the right continuous archives could find that anomaly, even if no single artifact survived. That leads directly to the next question. If machines and buildings are basically guaranteed to vanish, and only global chemistry stands a chance, what specific industrial materials and processes are most likely to leave a durable, recognizable signal in the rocks, one that no volcano or asteroid could easily fake? That is where you start looking hard at plastics, concrete, metals, and radionuclides, not as things you use, but as future fossils and chemical scars. Here's the blunt truth. The smartest things your species has ever built, the tech you're proud of, is not what the far future will see. They will see weird trash and broken chemistry. If industry has happened before on this planet, the only hard clues that survive are not phones, not satellites, not towers, but stubborn materials and distorted element ratios locked into rock. Start with plastics because they are already turning into a kind of future fossil. Plastics are long-chain polymers built from fossil carbon, tuned to resist decay. Sunlight, heat, and mechanical stress break them down, but they don't vanish. They fragment. Big pieces become smaller pieces, then microplastics, then nanoplastics. Those tiny fragments mix into soils, drift into rivers, sink through the water column, and end up in mud on lake beds and ocean floors. Once buried, they can sit there for very long times, trapped in layers that later harden into sedimentary rock. So the question is simple. If someone in the far future drilled into those layers, what would they actually see from plastics? Not as fresh bottles, but as part of a rock. They would find an unusual carbon-rich mix, synthetic polymers blended with natural organic matter, sometimes with specific additives like certain halogens or metal-based stabilizers that don't match normal biological patterns. That signal wouldn't show up evenly everywhere, but in the right basins, you could get a distinct horizon where the concentration of synthetic carbon spikes sharply compared to layers above and below. For a truly ancient industrial phase, that's exactly the sort of "this is not just normal mud" flag you would want. But plastics are only part of the story. What about the stuff you turn the whole surface into? The hard skin of cities, the concrete. Concrete is basically artificial stone. You take crushed rock and sand, mix it with cement made from heating limestone and clay, and add water. The result is a man-made version of a sedimentary rock, mainly calcium silicate hydrates, plus whatever filler and rebar you used. When concrete structures collapse, they don't revert to original sand and limestone right away. They break into chunks. Those chunks can be carried by landslides, rivers, and waves, and eventually get buried inside new sediments. Over enough time, you get urban rock, natural sediments that contain clasts or fragments of concrete, bricks, asphalt, and glass, mixed with normal pebbles. In a future outcrop, that might show up as a conglomerate where some of the stones are clearly artificial compositions, with shapes and internal textures you don't get from purely geological processes. Even if later heating alters the minerals, the bulk chemistry, like an unusually high calcium from cement or specific ratios of trace elements from industrial additives, can still betray that this was once construction material. For a past civilization, you wouldn't expect to find intact buildings, but you might find odd composite clasts in old conglomerates that don't line up with any natural rock type. Now, move to metals, because they are central to any serious technology, but they are also chemically active. Steel rusts fast when exposed to water and oxygen. Aluminum forms a thin oxide layer that protects it for a while, but over long times it still breaks down, especially in certain soils and waters. Copper and other base metals can dissolve, move through groundwater, and reprecipitate in new places, so you will not get shiny beams and cables surviving tens of millions of years near the surface. The thing that can survive, though, is the way you disturb ore bodies. Industrial mining pulls huge amounts of metal-rich rock from deep, concentrated deposits, spreads that material out on the surface, and concentrates waste in tailings piles. That rearrangement can leave crustal-scale anomalies, zones where certain metals are unusually depleted in their original source and unusually enriched in sediments. If another civilization did large-scale mining, the pattern of missing ore in some layers, plus weirdly enriched fine sediments in others, could be a clue. On top of that, some alloys use element combinations nature almost never assembles alone. Even if the alloy corrodes, the unusual blend of trace elements might still be detectable in the solidified remains. There's an even cleaner signal, and it comes from radioactivity. High-tech civilizations can dig up and process radioactive elements. They can run reactors. They can test nuclear weapons. They can accidentally release nucleoradioisites. Some of these isotopes are short-lived and vanish quickly, but others decay slowly, and their daughter products, the elements they decay into, stick around in known ratios. A burst of nuclear activity can leave a fingerprint, a specific combination of isotopes and daughter products in soils and sediments that looks very different from the gentle background changes caused by natural uranium and thorium decay, or by cosmic rays. For your own time, people are already talking about the plutonium signal and similar markers as part of a possible Anthropocene layer. In a deep time scenario, many of the original unstable isotopes would be gone, but the pattern of stable daughters and certain rare isotopes could still tell a story. A geochemist millions of years from now, or a geochemist on some other world, could look at those ratios and say, something at this moment artificially shuffled the nuclear deck. So if you combine plastics, urban rock, metal anomalies, and radioactive traces, what does a real detection plan look like? You would not walk around looking for intact gadgets. You would not hope for a fossilized car or a preserved circuit board. You would run chemical and isotopic surveys on deep cores from places with continuous sedimentation. You would search for horizons where several things change together: a sudden appearance of synthetic or heavily modified polymers, a jump in heavy metal patterns, a distinct shift in carbon and nitrogen isotopes that matches large-scale fossil fuel burning and fertilizer use, and a spike in anthropogenic radioactives or their decay signatures. The key concept is unnatural ratios and sudden introductions. Nature can spike carbon dioxide through volcanism or methane from large-scale biological events, but those events have characteristic isotopic fingerprints. Nature can concentrate metals, but does so in ore deposits with specific geological settings. Nature can change nitrogen cycling, but usually tied to gradual ecosystem shifts. When you see a narrow time window where multiple element cycles are hit at once in directions that line up better with industry than with known natural mechanisms, that is when you start talking seriously about a tech spike. And here's the part that should bother you. That same toolkit is exactly what any alien scientist would use to judge whether Earth ever hosted a civilization, including yours. They would not see your skyscrapers or your internet. They would see a thin band, maybe a few inches thick, where the chemistry goes insane compared to the rest of the core. If they find that, you are real to them. If they do not, you are just another brief biological experiment that never left a clear mark. So the next logical step is to ask, what drives those global chemical changes at the deepest level? What physical constraint forces any advanced civilization to push enough energy through its world that it risks turning its own activity into a planet-scale disaster signal? That's where you have to talk about waste heat, atmosphere, and the hard limits of running a high-energy society on a fragile, finite planet. You can argue about energy policy all day, but do you notice the one thing you don't get to choose, no matter who's in charge? Every bit of energy you use, every watt, has to end up as heat. That's physics. A civilization that runs on fire, engines, data centers, and industry is basically a giant machine for turning concentrated energy into low-grade waste heat spread through its environment. You can delay where it goes, you can move it around, but in the end, it all shows up as extra thermal load on your world. At the scale of one house or one city, that doesn't sound like much. At the scale of a planet, if energy use climbs high enough, waste heat itself becomes a form of climate forcing. Even before you talk about greenhouse gases, just the raw heat dumped by massive energy use can warm the environment. That means any advanced civilization that keeps pushing growth will eventually run into a hard wall, where its own energy use starts to change the climate in obvious ways. In data terms, that looks like a sharp change in temperature trends, out of line with normal orbital cycles or volcanic activity, compressed in a short time window. Now, add the greenhouse gases on top of that. You are not just releasing heat, you are changing the way the planet keeps heat in. Carbon dioxide and methane trap outgoing infrared radiation, thickening the thermal blanket around the planet. If you release them slowly over millions of years, ecosystems and rock weathering can adjust. If you release them quickly over centuries or less, you shock the system. The atmosphere does not care whether the carbon came from volcanoes or engines, but the pattern in the rocks can show the difference. Here's the key. Rapid rises in carbon dioxide and methane leave isotope signatures. Carbon comes in slightly different masses, lighter and heavier versions. Life prefers the lighter version, so organic carbon and fossil fuels have a distinct ratio. When you dig up and burn huge amounts of fossil carbon, you inject a lot of light carbon into the atmosphere and the oceans. Later, that carbon gets locked into shells, carbonates, and organic sediments. A geologist millions of years from now can measure those ratios and see a sudden swing toward lighter carbon at a specific level. That is exactly the kind of signal you would look for if you were testing the idea of a brief, intense industrial phase. But carbon is only part of the story. Think about nitrogen, the backbone of fertilizers. Under natural conditions, nitrogen cycles between the atmosphere, soils, and living things at a certain pace, driven mostly by microbes and lightning. Industrial civilization hacks that cycle by pulling nitrogen from the air using high-temperature, high-pressure chemistry, then spreading that reactive nitrogen on fields. That extra input runs off into rivers, lakes, and coastal waters, changing ecosystems and boosting algae and bacteria in ways that are not normal for the planet's past. Just like carbon, nitrogen has isotopes, and natural processes sort them in specific ways. Industrial fixation and heavy fertilizer use can shift the balance, especially in sediments where dead algae and organic matter build up. Over time, those sediments turn into rock, locking in a pattern of nitrogen isotopes that says, in this interval, the planet's nitrogen cycle was pushed hard in a way that does not match ordinary biology or slow geological change. So, if you were checking for an earlier industrial run, you wouldn't just measure carbon. You would also look for a linked nitrogen anomaly, pointing to large-scale artificial fertilization or something similar. Now look at fire. A fossil-fueled civilization burns. A lot. Power plants, engines, heating, land clearing, wildfires triggered by climate shifts. All of that creates soot, tiny black carbon particles that can travel far in the air and settle out over wide regions. In ice cores and sediments, those particles show up as dark layers or spikes in black carbon content. Volcanic eruptions can also add particles, but they tend to have different chemical signatures and come with big sulfur spikes and distinct ash. Human-scale combustion, especially spread over many sources worldwide, makes its own pattern. This matters because soot is linked to both warming and cooling episodes. It can darken snow and ice, making them absorb more sunlight and melt faster, or it can block sunlight in the atmosphere for a time. If you step back and see the whole picture, a planet going through a civilization-driven burn phase could show a combination of rising greenhouse gases, rising temperatures, shifting isotopes, and occasional soot spikes tied to intense burning, forest loss, and industrial accidents or wars. In rocks, that compresses into a narrow band with unusual carbon, nitrogen, and black carbon levels, all aligned in time. Put these pieces together and ask a direct question. What would a planet-killing civilization actually look like? Not in stories, but in numbers. You would see a fast, steep climb in energy use, traced by waste heat and greenhouse forcing, pushing global temperatures off their normal path. You would see rapid changes in atmospheric chemistry, especially carbon dioxide and methane, marked in isotope ratios. You would see nitrogen cycles distorted by industrial fixation, and you would see widespread combustion leaving black carbon as a fine line in ice and sediments. If things went badly enough, you might also see a linked mass extinction, ocean chemistry collapse, or widespread oxygen loss recorded as black shales and sharp biodiversity drops. Here's the punchline. Any truly global civilization, not just one city or one region, but a species that builds a high-energy network over a whole planet, automatically risks writing its own epitaph in its atmosphere first, and then in its rocks. It has no way to use huge amounts of energy without creating waste heat. It has no way to burn fossil fuels without shifting carbon isotopes. It has no way to feed billions with synthetic fertilizer without twisting nitrogen patterns. And it has no way to run that entire system without leaving a soot and pollution footprint. The only question is how long the spike lasts and how hard it crashes. That should change the way you look at both your own situation and the rest of the universe. When you look up and see no obvious signals, it may not mean no civilizations have ever existed. It may mean that most civilizations hit this energy trap, push their planet into a narrow, violent data spike, and either stabilize at a lower level or fail, leaving behind a thin, strange layer that later observers have to work hard to notice. So, the next step is to ask what actually happens to life when a planet crosses those lines, when climate and chemistry swing so fast that ecosystems cannot keep up. You already have a set of real case studies on Earth, not from industry, but from nature, where the planet itself triggered disaster modes that wiped out most species and reset the board. To understand how fragile a civilization really is, you have to look straight at those events, the big mass extinctions, and see what kinds of changes the planet is actually capable of pulling off on its own. How many times has Earth already run the kind of crisis that would end you, your cities, and everything that depends on stable climate and oceans? The uncomfortable answer is more than once, and the planet did it without any help from technology. When you look at the big 5 mass extinctions in the rock record, you see a pattern that should make any civilization feel temporary. Across those events, times, different continents, different species, the same core correlations keep showing up. There's a sharp climate shock, often a rapid warming or cooling far outside normal swings. There's a major change in ocean chemistry, things like acidification or loss of dissolved oxygen. There are changes in the atmosphere, greenhouse gases going way up or down, aerosols cutting sunlight, or strange sulfur and carbon signatures. And laid on top of all that, there's a sudden drop in biodiversity, whole groups of organisms disappearing in a relatively small slice of time. Take the end Permian extinction, often called the Great Dying. Around 90% of marine species and a huge fraction of land species vanished. The data point to massive volcanic activity in what is now Siberia, releasing huge amounts of carbon dioxide, methane, and other gases. Temperature spiked, oceans warmed and lost oxygen, and ecosystems collapsed. Different event than the later asteroid strike that hit at the end of the Cretaceous, but the pattern rhymes. Fast climate change, stressed oceans, disrupted atmosphere, and then a crash in life. So what actually does the killing in physical terms? Several mechanisms scale to the entire planet. One is darkness from aerosols and dust. Large eruptions or impacts can throw huge amounts of fine particles into the stratosphere. Those particles block sunlight for months or years. Photosynthesis drops, land plants and ocean plankton suffer, and everything up the food chain feels it. Another mechanism is acid rain and ocean acidification. Sulfur and nitrogen gases from volcanoes or burning can form strong acids in the air. They fall with rain, damage soils and fresh water, and push surface oceans toward more acidic conditions, which is brutal for anything that builds shells or skeletons from calcium carbonate. Then there's hyperwarming, rapid and extreme warming driven by greenhouse gas spikes. This shows up in several of the big extinctions. Warmer oceans hold less oxygen, circulation patterns change, and deep waters can turn anoxic, meaning they lose oxygen almost completely. That leads to ocean oxygen loss as a kill mechanism. Many marine organisms cannot survive low oxygen. Once they die off, food webs collapse, both in the sea and on land, because so many land animals depend on marine productivity, directly or indirectly. You end up with a stacked set of stressors: less light, more acid, less oxygen, and cascading food failure. Here's the key point for the civilization question. These mass extinctions prove that you do not need technology to generate extreme signatures in rocks. Nature can do it on its own. Large igneous provinces, where huge volumes of lava and gas erupt over hundreds of thousands of years, can inject enormous amounts of carbon dioxide and other gases into the atmosphere. Asteroid impacts can deliver an instant energy pulse and throw up dust and vaporized rock. Tectonics can rearrange continents and oceans, changing currents and climate. So when you see a big extinction and a big chemical spike in the record, you cannot just say, civilization did this. You have to separate natural spikes from any hypothetical artificial ones. That is why geologists look very closely at the details. In natural events, the pieces line up with known physics. For a big lava province, you find huge basalt layers, patterns of certain volcanic gases, and isotope shifts that match mantle sources. For an impact, you find a crater, shocked minerals, and a specific mix of elements like iridium. For long-term tectonic changes, you see gradual shifts in sediments and fossils. If you ever found a mass extinction with a chemical pattern that did not match any of those natural mechanisms, then you would have a real mystery. Right now, every one of the big five can be explained with natural drivers, even though they're violent enough to erase complex ecosystems. So what do the rocks actually preserve best from these disasters? They keep clear, repeated signals of sudden biodiversity drops. You see diverse fossil assemblages below a boundary, then simplified, stressed communities above it. You see carbonate dissolution horizons, layers where ocean acidification ate away at carbonate sediments, leaving signs that the chemistry of seawater crossed a threshold. You see black shales, organic rich sediments that form when bottom waters lack oxygen and dead material piles up without fully decaying. You also see global isotope excursions, sharp planet-wide shifts in things like carbon and sulfur isotope ratios, locked into shells and minerals. Put those together and you get a short checklist. A classic mass extinction layer often has a strong, narrow shift in carbon isotopes, a drop in fossil diversity, evidence for oxygen-poor conditions in the oceans and sometimes clues to the trigger, like volcanic ash or impact ejecta. That is the extreme event pattern the planet knows how to produce on its own. Any serious search for civilization signatures has to respect that and look for patterns that go beyond what volcanoes and impacts can do. So here's the connection that matters for you. If a technological civilization existed in the past, and if it pushed its world too hard, these are the same planetary modes that would wipe it out. Rapid greenhouse gas injection and warming, oxygen loss in the oceans, acidification, darkness from aerosols, and food web collapse are exactly the kinds of stress that would crush global agriculture, fisheries, and industrial supply chains. A smart species might trigger those modes through fossil fuel burning, uncontrolled industry, or large-scale landscape change. But once the system tips, it doesn't care why it was pushed, it just runs the physics. For our planet, that means the Big Five are not just history lessons, they're worked examples of how a world removes complex life at scale. Each one shows how far Earth can swing in climate and chemistry, and how quickly it can turn a thriving biosphere into a much poorer one. If you place a civilization inside one of those swings, its lifespan becomes tightly constrained. It has to either avoid triggering those conditions or somehow ride through them while its food sources and ecosystems fail. The next logical question is, what does a single, well-studied civilization ender actually look like, where you can trace the whole chain from impact to darkness to extinction? You already know the name of one of them because it's the event that ended the age of non-bird dinosaurs. To see what a real hard reset looks like in data, you have to look closely at the Chicxulub impact, the crater it left, the layers it produced, and the months and years after the hit, when the sky went dark and the surface of the planet became almost unfriendly to anything that needed light and stable climate. A single rock slams into Earth once, in the wrong place, at the wrong speed, and an entire world order ends. That's not theory. That's what happened at the end of the Cretaceous, and the scar is still there. The Chicxulub crater, mostly buried under the Yucatan Peninsula and the Gulf of Mexico, is about 110 miles, 180 kilometers across. The object that made it was probably around 6 to 9 miles, 10 to 15 kilometers wide, moving at tens of thousands of miles per hour. In a few seconds, it released more energy than billions of nuclear weapons going off at once. For any complex biosphere and for any civilization, that scale of input is beyond normal planning. Start with the first seconds to minutes, because that's the raw impact physics. The asteroid hits shallow ocean and crust, vaporizes rock and water, and blasts out a cavity that collapses into a huge crater. Shock waves radiate through the crust, producing mega earthquakes far larger than anything in recorded history. Close to the impact, everything is just gone. Rock, water, atmosphere, all stripped and thrown aside. Further out, but still on the same continent, the airshock flattens forests, rips apart animals, and throws debris at extreme speeds. Tsunamis race outward, hundreds of feet high, hitting coasts around the Gulf and beyond. If you had cities within thousands of miles, they would not just be damaged, they would be completely removed. That is only the local part of the kill chain. The global damage really begins when the ejecta comes back down. The impact throws molten and solid fragments of rock high above the atmosphere. As these fragments fall back through the air all around the planet, they heat up from friction. That heat radiates downward, and for a short time, the upper layers of the atmosphere and even parts of the surface are heated enough to trigger wildfires on land. There is evidence that huge areas of vegetation burned. Anything on the surface that cannot escape heat and fire is in serious trouble. Oceans get hit by waves and hot fallout at the same time, adding to the chaos. Then, the atmosphere itself takes over as the primary weapon. The impact pulverizes rock rich in sulfur and carbonates, blasting fine dust and sulfate aerosols high into the stratosphere. That layer is above most of the weather, so material can stay there for years. Dust and aerosols block and scatter sunlight. At the surface, light levels drop sharply. Global temperatures fall. Photosynthesis, on land and in the oceans, collapses. The term for this is impact winter. It is not poetic, it is a direct description of what happens when you cut off most sunlight to a system that depends on it. Think about your own world under that. Crops fail because the growing season is too cold and too dim. Forests and grasslands, already hit by fire, now have to regrow with less light. In the oceans, phytoplankton, the tiny plant-like organisms that form the base of the food chain, stop working properly. Once they decline, everything above them, from small fish to large predators, loses its food supply. You get a wave of starvation that moves from primary producers up to herbivores and then to top predators. Big animals with high food needs, like non-bird dinosaurs on land, lose in that game. The key feature is timing. On geological scales, the impact and the immediate firestorm are almost instantaneous. The climate and food chain effects play out over years to decades. That is long enough to kill off generations of large animals, but short enough that in the rock record, it looks like a sharp break. Below a thin layer, you see a diverse, stable ecosystem. Above it, a very different mix of species, missing many large forms, with new groups starting to spread. The point is, a single day's event can produce a multi-year shock that looks like a hard reset when you see it compressed in rock. How do we know Chicxulub is the culprit and not just a coincidence? The evidence package is very specific. At the boundary between Cretaceous and Paleogen rocks, in many locations worldwide, you find a thin, clay-rich layer. In that layer, there is a spike in iridium, a rare element in Earth's crust, but more common in some types of meteorites. You also find shocked quartz, grains that have been deformed by sudden, intense pressure, which normal tectonics cannot easily produce at that scale. There are tiny glassy spheres and tektites, droplets of rock melted and thrown into the air, then cooled as they fall. All of this sits exactly at the level where dinosaur fossils disappear. Below that boundary, you have abundant fossils of non-bird dinosaurs and many other species. Above it, you have a different fauna, with mammals beginning to expand. The crater itself matches the age of the boundary layer. Drilling into the Chicxulub structure shows impact melt rocks and a shape consistent with a massive collision. When you line up the crater age, the iridium anomaly, the shocked minerals, and the fossil change, the impact explanation is not just plausible, it is the only one that fits all the data at once. That is why scientists call it a smoking gun for that extinction. Now put a civilization into that picture, one with satellites, global trade, high-tech infrastructure, and reliance on large-scale agriculture. How much does that really help against this kind of event? You might see the object early with telescopes. If you had enough warning and the right technology, you might try to deflect it. But if you fail, or if the object is only noticed late, the physics is the same. Near-impact zones are erased. Coastal cities are struck by tsunamis. Global communication networks, ports, and industrial hubs are heavily damaged. Even if some technology survives outside the worst zones, the impact winter is the real long-term threat. Less sunlight means less power for solar systems. Colder temperatures and shorter growing seasons mean repeated crop failures on multiple continents. Supply chains break as transport networks are damaged and food exporting regions fail. Fish stocks crash as ocean productivity drops. You cannot feed billions of people in that environment with normal agriculture. And unlike dinosaurs, you rely on global logistics, complex chemistry, and just-in-time systems that are not designed for multi-year shock. The key point is harsh. Even a high-tech society cannot simply engineer around a multi-year loss of reliable sunlight and climate stability on a global scale. You can build bunkers, you can store some food, you can shelter a fraction of the population, but you cannot keep a planet-wide industrial system running at full scale when the base of the food chain is hit everywhere. The ending is not the instant of impact. The ending is the months and years afterward, when slow starvation and long-term climate and ocean damage finish what the rock started. From a data perspective, a civilization caught in a Chicxulub-style event would leave a combined signal, the natural impact signature, plus any industrial chemical anomalies that were already in progress. A future geologist might see a tech spike in carbon and nitrogen isotopes, plastics, and metals cut off sharply right at the impact layer. That would look like a civilization that was interrupted by an external blow, literally wiped off its path by a single object from space. So far, you have seen one clear external reset tool the universe uses, a big asteroid. But it is not the only one you need to worry about. There is a slower but just as dangerous version that comes from inside the planet itself. Instead of a rock hitting you from above, you get magma and gas rising from below, on a scale big enough to change climate, chemistry, and agriculture for years to decades. If a rock can almost end a biosphere in one day, what does it look like when the planet spends centuries venting poison and dust on its own surface? A planet does not need an asteroid to wreck its climate. It can do it from the inside, in a single eruption that keeps throwing consequences at you for years. Supervolcanoes are that version of the threat, slower than an impact in the first minutes, but just as dangerous for a civilization that depends on stable weather and tight supply chains. Take the Toba eruption as a benchmark. The youngest Toba event, about 71,000 to 74,000 years ago, blew out an estimated 670 cubic miles of material. That's roughly 2,800 cubic kilometers. Try to ground that in real terms. That's enough volcanic debris to cover an entire state in the United States under hundreds of feet of ash. It carved out a massive caldera that is now Lake Toba, and it threw ash and gases high into the atmosphere, far beyond normal eruptions you see in modern history. Human groups at that time were small and scattered, and there's debate about how much Toba stressed them, but the key point is simple. This is a scale of eruption that a modern civilization has never had to face directly. So if that much material is suddenly injected into the system, what does it actually do to the planet's climate? The main lever is not the ash you see on the ground. It's the sulfur-rich aerosols that form in the stratosphere. When a supervolcano releases sulfur gases, they react in the upper atmosphere to form tiny droplets that are very good at reflecting sunlight back into space. That cuts the amount of solar energy reaching the surface. Temperatures drop. This is aerosol-driven cooling, and it can last for years because those droplets sit above most of the rain that would normally wash particles out of the air. Once you cool the surface and change the way sunlight hits different regions, major circulation systems start to shift. Monsoons, which depend on strong temperature contrast between land and ocean, weaken or move. Rain belts shift away from some agricultural zones. Growing seasons shorten. You do not need a deep freeze to hurt civilization. You just need a few degrees of cooling at the wrong time of year across large food-producing areas. That's enough to cut harvests year after year while you're already dealing with ash and social disruption. But even before you feel the full climate effect, there's a more direct hit. Ash is infrastructure kryptonite. Fine ash particles are sharp, abrasive, and electrically active. They clog air filters, scratch moving parts, and conduct electricity when wet. Jet engines can stall and fail if they fly through ash clouds. Power lines can short and collapse under ash load. Roads become slippery and hard to clear. Water treatment plants and distribution systems can be overwhelmed by ash-contaminated runoff. You get a long list of things that were modern and reliable under normal conditions, suddenly turning fragile under a heavy ashfall. Look at the small eruptions we've actually seen in recent decades, like the 1980 Mount St. Helens eruption, or the 2010 Eyjafjallajökull eruption in Iceland that disrupted air traffic. Those were tiny compared to Toba-scale events, yet they still managed to shut down airports, damage machinery, and stress local infrastructure. Scale that up by orders of magnitude, and you're in a world where entire regions lose power, transportation, and clean water at the same time, while they're trying to coordinate an emergency response under darkened skies. So if the land and the sky are taking immediate damage, are the oceans safe in the short term, or do they have their own delayed crisis built in? The oceans respond more slowly than the atmosphere because water has a high heat capacity, and deep mixing takes time. But that delay is exactly why the problems can persist. Cooling at the surface changes density patterns and circulation. Some currents weaken, others reroute. Nutrient upwelling zones can shift, stressing fisheries. In some scenarios, you get surface cooling but deep waters that stay relatively unchanged, which can alter oxygen distribution and push some regions toward low oxygen conditions. When the aerosols finally clear and sunlight returns to more normal levels, the land surface may start to warm again, but the ocean circulation changes can last much longer. That can mean prolonged stress on marine ecosystems, even after the visible volcanic winter is over. Coral reefs, plankton communities, and fish stocks can struggle to recover from a combined hit of temperature swings, acidification from extravolcanic CO2, and disrupted circulation. For a civilization that relies on oceans for food and trade, that lag matters because it extends the crisis beyond the obvious sky-darkening phase. Now connect all of this back to a high-tech society. Do you actually need a full mass extinction to knock civilization down, or is something less than that enough? The answer is you don't need extinction at all. You only need multi-year harvest failure plus system fragility. Modern societies are built on just-in-time logistics, globalized trade, and tight coupling between energy, food, and finance. If a supervolcano cuts sunlight, cools key agricultural regions, disrupts monsoons, and drops ash on major infrastructure, you get repeated bad harvests, fuel shortages, and broken transport networks at the same time. In that scenario, stored grain and emergency plans buy you some time, but not unlimited time. Conflicts over remaining resources can break out. Countries that depend on food imports find themselves suddenly exposed when exporting regions can't spare surplus. Internal power grids fight to stay up under ash load and lower demand, while fuel supplies are constrained. The complexity that makes your civilization powerful also makes it brittle when too many subsystems fail at once. From a deep time point of view, what would a Toba-scale eruption do to the rock record during a technological era? You'd likely see a volcanic ash and aerosol signal, a short-term cooling episode in climate proxies, and maybe a knock in biological indicators like pollen and marine microfossils. If industry is active at the same time, you might see that volcanic signal layered on top of or interacting with an existing tech-driven carbon and nitrogen anomaly. To a future geologist, it might look like a civilization already stressing its planet, then taking a hard hit from underneath. And here's the part that tightens the picture. Supervolcanoes and impacts are not the only large switches the planet can flip. Even without a big blast from above or below, the climate system and the oceans can slide into deadly modes on their own, especially if they're already pushed by greenhouse gases or other disturbances. One of the most dangerous of those modes is much quieter than an eruption. It doesn't come with a single loud day. It comes with years to centuries of oceans slowly losing oxygen and turning into hostile zones that leave a clear black signature in the rocks. How do you turn an entire ocean into a death zone without a single bomb, without an impact, without any loud event at all? You warm it. You feed it too much, you let chemistry do the slow work, and then one day, most of the water that feeds your planet is hostile to complex life. The basic mechanism is simple, and that is what makes it scary. Warm water holds less dissolved oxygen than cold water. As the climate warms, surface oceans take in less oxygen from the air. At the same time, if nutrients spike, from rivers, from fertilizers, from weathered rock, from upwelling, you get huge blooms of algae and plankton near the surface. At first, that looks like life exploding, lots of microscopic plants and tiny animals feeding in sunlit layers. Then they die, and their remains start to sink. Bacteria move in and begin to break down all that organic matter. That decay uses up oxygen in the deeper water. If mixing is weak, if fresh oxygenated water from the surface does not reach those depths fast enough, oxygen levels drop, then crash. You go from low oxygen to no oxygen, from hypoxic to anoxic. Once that happens over large areas, big parts of the ocean turn into zones where fish, shellfish, and many other organisms simply cannot survive. The rock record shows you exactly what those conditions look like after the fact. When bottom waters lack oxygen, dead organic matter is not fully broken down. It piles up in the mud and gets buried. Over time, those layers turn into dark, organic-rich sedimentary rocks called black shales. They are literally black because they contain so much preserved carbon. In past events, known as oceanic anoxic events, you see widespread black shales of similar age on different continents, telling you that large chunks of the global ocean went oxygen poor at the same time. Those black shales are not subtle. They say, right here in time, the ocean stopped breathing properly. They also matter for another reason. Under the wrong conditions, oxygen-poor water can turn into something even worse, euxinic water, where hydrogen sulfide builds up. Hydrogen sulfide is a toxic gas, deadly to most complex life at high concentrations. In some past intervals, scientists think that hydrogen sulfide may have leaked out of deep, stagnant basins, reaching shallower seas and even the atmosphere near coasts. That is not just bad for fish. Hydrogen sulfide can damage plant tissues, animal lungs, and the ozone layer. If those conditions spread, you get a planet where coasts are sometimes bathed in poisonous air and large stretches of ocean are biologically hollowed out below the surface. Even if not every ocean goes fully euxinic, large persistent anoxic zones alone are enough to wipe out many species and severely damage marine ecosystems. Now, translate that into human terms. Right now, oceans provide a huge fraction of the protein for billions of people through fisheries and aquaculture. They also support global trade with shipping routes that depend on stable weather and functioning ports. If anoxia spreads in modern oceans, fish populations crash or shift in ways you cannot easily predict or manage. Coral reefs bleach and die under combined stress from warming, acidification, and low oxygen. Dead zones expand, turning once productive fishing grounds into barren water. When marine food webs fail, you don't just lose some fancy seafood in rich countries. You hit the basic diet and income of entire regions. Nations that rely heavily on fish exports or local catches for food security suddenly face shortages, prices spike, people move. You can fight a war, you can negotiate peace deals, you can sign treaties, but you cannot negotiate with dead oceans. You cannot talk low oxygen water into carrying more fish. You cannot convince hydrogen sulfide not to form if the chemistry and physics say it will. Once big parts of the sea flip into a different state, your options narrow to adaptation and damage control. And both are harder the more your civilization depends on a steady, predictable ocean. In the rock record, an ocean anoxia crisis shows up as more than just black shale. You see changes in sulfur and iron chemistry because different minerals form when oxygen is missing. You see shifts in nitrogen isotopes because microbial processes in low oxygen water sort nitrogen differently. You often see linked carbon isotope anomalies because burial of all that organic carbon alters the global carbon cycle. And you see fossil evidence, lineages of marine organisms shrinking or disappearing, new forms struggling to take over in stressed conditions. If an industrial civilization helped drive an ocean anoxia event, its fingerprints would sit on top of that natural pattern. You would expect to see, right before or during the expansion of black shales, a spike in carbon isotope values that match massive fossil fuel burning, nitrogen isotope changes consistent with industrial fertilizer, and maybe metal and plastic traces in coastal sediments. The natural and artificial signals would overlap, but the combination and the timing would tell you that this was not just a slow tectonic or volcanic shift. Something intelligent pushed the system toward the edge. In that sense, ocean anoxia is both a natural kill mechanism and the potential endgame for a civilization that does not manage its energy and nutrient flows. You don't need an asteroid. You don't need a global war. You only need enough warming, enough nutrient loading, and enough time for feedback loops to eat away at oxygen. Once the deep basins go anoxic, even if the surface still looks blue and calm from space, the biosphere underneath is in serious trouble. And that brings you to another layer of risk, because oceans and atmosphere don't operate separately. When you change one hard enough, the other follows. The same processes that strip oxygen from water, that bury organic carbon, that release or consume gases, also alter the composition of the air above. In Earth's past, there have been times when the basic makeup of the atmosphere itself flipped, turning what used to be normal for life back then would kill you now, and what you call normal today would have killed almost everything then. The Great Oxidation Event is the clearest proof that a planet can rewrite its own air. Go back roughly 2.46 to 2.06 billion years. Before that window, the atmosphere had almost no free oxygen. Microbes ran the show, using chemistry that didn't need oxygen, and methane was likely a major greenhouse gas keeping the planet warm under a fainter sun. Then, photosynthetic microbes, the ones that split water and release oxygen as a waste product, had enough time and space to change the global balance. Oxygen started to build up in surface waters and in the air. From your point of view, more oxygen sounds like a good thing. You need it every second. But for the dominant microbes of that era, oxygen was a toxin. Their enzymes and cell structures were not built to handle it. As oxygen levels rose, a lot of those organisms were pushed into shrinking low-oxygen niches, or wiped out. The chemistry of Earth's surface shifted. Minerals that had stayed in reduced form started to oxidize. Iron dissolved in seawater began to combine with oxygen and drop out as solid iron minerals. This is why the Great Oxidation Event matters so much. It shows that a major gas shift can crash the dominant life forms without any asteroid or supervolcano. If the basic composition of the air changes fast enough, normal becomes lethal. Entire groups of organisms lose their core energy systems. Metabolic pathways that used to work suddenly produce damaging byproducts. The biosphere has to resort itself around a new chemical baseline. For that ancient world, oxygen was the revolution, and it hit hard. There's another twist here that ties straight into climate. Before oxygen rose, methane from microbes helped keep the planet warm. Methane is a strong greenhouse gas. When oxygen increased, it reacted with methane, destroying it faster and reducing its concentration. If methane drops quickly, the greenhouse effect weakens. Less heat is trapped and the planet cools. There is evidence that after the rise of oxygen, Earth fell into long glaciations, sometimes called the Huronian glaciations. Once ice sheets grow, they reflect more sunlight back into space. That makes cooling stronger, which can let ice spread even more. This is a feedback loop. A gas change in the air, driven by microbes, can push the climate toward large-scale glaciation, maybe even near snowball conditions where ice reaches low latitudes. No war, no advanced tech, just basic biology plus physics, rearranging both air chemistry and climate. So what do you actually see from all of this in the rocks, billions of years later? You do not see the microbes directly most of the time. You see their chemical footprints. One key sign is banded iron formations, layers of iron-rich minerals alternating with other sediments. These form when dissolved iron in seawater combines with oxygen and precipitates out. Large deposits of these rocks line up with times when oxygen first started to rise in the oceans. You also see red beds, sedimentary rocks stained by iron oxides, the same general kind of rust that forms when iron meets oxygen. Those red colors tell you that by the time those sediments were laid down, the atmosphere and surface waters had enough oxygen to oxidize iron on land and in rivers. On top of that, you see distinctive shifts in sulfur isotopes. Before the Great Oxidation Event, sulfur chemistry in the atmosphere produced certain isotope patterns that are hard to maintain once oxygen is abundant. After oxygen rises, those patterns change. That gives you a before and after line in the rock record, a chemical story on a planetary scale. All of this is important for civilization for a simple reason. Your technology assumes air chemistry stays within a narrow range. Engines, turbines, electronics cooling systems, human lungs, crops, ocean fisheries. All of them are tuned to today's mix of nitrogen, oxygen, water vapor, and trace gases. You can handle small swings in greenhouse gases. You can adapt to a degree or two of warming or cooling if you have time and resources. But if the planet ever runs a major gas shift again on the scale of the Great Oxidation Event, the entire support system for your technology becomes uncertain. Even smaller, faster gas shifts can hurt you badly. If carbon dioxide doubles or triples in a short geological time, you get large warming, ocean acidification, and stressed ecosystems. If methane spikes and then collapses, you get rapid swings in climate that infrastructure and agriculture are not built to track. If oxygen in the oceans drops significantly, you hit fisheries. If oxygen in the atmosphere were ever to swing by more than a few percent in either direction, fires, metabolism, and corrosion rates would all change. The point is not that the exact great oxidation event will repeat. The point is that Earth has already shown it can rewrite its atmosphere enough to restructure life. From a deep time perspective, atmospheric revolutions leave a different set of marks than impacts or supervolcanoes. You see long-term trends in red beds, iron formations, sulfur isotopes, and carbon cycles. You see big shifts in the kinds of minerals that can exist at the surface. You see ecosystems reorganize as some metabolisms vanish and others spread. If a technological civilization ever lived through or caused a sharp atmospheric shift, its signature would be layered into that chemical pattern. Synthetic compounds, odd metal ratios, or nuclear byproducts would ride on top of the broader gas change signal. For you, the harsh takeaway is that the planet does not guarantee stable air chemistry just because your power grid needs it or your lungs prefer it. If your tech pushes the atmosphere hard enough, or if long-term feedbacks kick in, the rules can change. A world that feels safe and familiar on century timescales can look very different over millions of years, and the rock record has already logged at least one full rewrite. And there's a concrete link to the next level of risk. When gas composition and greenhouse strength shift enough, and when feedbacks like ice and albedo get involved, you don't just get unusual weather. You can lock the entire planet into deep freeze states for millions of years. That has happened more than once. For a civilization that needs open oceans, ice-free ports, and global shipping, a planet-scale freeze is not just a cold snap. It's a complete knockdown of logistics, metals extraction, and energy systems. So the next step is to look at what happens when those feedbacks run all the way to the edge, when ice spreads so far that almost the entire surface of the planet locks up, and life is pushed into few harsh refuges under the ice and within it. Here's a question that should bother you. How does a planet go from open oceans and active life to almost completely frozen over and then back again without staying dead forever? That's not a science fiction scenario. That's Earth during the Cryogenian period, roughly 720 to 635 million years ago, when major Snowball Earth events hit. Evidence points to at least two big global glaciations in that window. Ice sheets didn't just sit at the poles, they likely pushed into low latitudes, maybe even close to the equator. For long stretches of time, the surface looked more like a frozen moon than the planet you know now. You need a strong driver to pull a whole planet into that state, and the main one is brutally simple: the albedo feedback. Albedo is how much sunlight a surface reflects. Ice and snow have high albedo. They bounce a lot of incoming energy back to space. Dark ocean water and rock have low albedo. They absorb more heat. Start with some cooling, from lower greenhouse gases, changes in continents, or less solar output. Ice grows from the poles toward lower latitudes. As ice spreads, more sunlight gets reflected. The surface cools further, and the ice front can move even closer to the equator. That loop, more ice, more reflection, more cooling, is the albedo trap. Once you pass a certain threshold, the system runs away into deep freeze. You might ask, why doesn't the planet just stabilize somewhere in between? On a world with continents crossing different latitudes, there are points where ice line feedbacks can be stable, but if you push past them, the ice edge can jump quickly. When ice covers most of the ocean, evaporation drops, rainfall patterns change, and the normal carbon cycle, where weathering pulls carbon dioxide out of the air, slows down. You end up with a planet where the surface is locked in ice for millions of years, while volcanic activity below still releases greenhouse gases. Heat from below and trapped gases slowly build a way out, but that takes geological time. So, in a snowball state, does life just stop? No, but it gets squeezed into narrow survival niches. Under thick sea ice, you can still have pockets of thinner ice or open water, especially near volcanically active regions or where currents push heat upward. Those areas, sometimes called polynyas, could support limited photosynthesis and food webs. Hydrothermal vents on the seafloor keep pumping chemical energy into the deep ocean, feeding microbes that do not rely on sunlight at all. Melting during parts of the year or in certain zones creates small liquid habitats, like meltwater ponds on or within the ice. Life hangs on in these refuges, but from a global perspective, the surface becomes a desert of ice, with complex ecosystems heavily suppressed. From a rock point of view, you do not see the ice directly anymore. You see its effects and its ending. One of the clearest markers of snowball episodes is cap carbonates. These are unusual carbonate rock layers that sit directly on top of glacial deposits. The picture is, after millions of years of ice cover, carbon dioxide from volcanoes has built up in the atmosphere because weathering and plant uptake were weak. When warming finally overwhelms the albedo feedback, the ice melts relatively fast on geological timescales. Warm, CO2-rich conditions drive intense chemical weathering and carbonate precipitation. The result is a sharp, thick carbonate layer capping the glacial sediments, a geological receipt for abrupt climate whiplash. You can also see drop zones, large clasts carried by ice and dropped into fine sediment as icebergs melt, and rocks that formed at low paleolatitudes, implying ice rafts were present in places that should have been warm. Isotopic clues line up too. Carbon isotope records show big swings, as long-term carbon cycling is interrupted and then restarts under very different conditions. Together, these signals say the planet went into a hard freeze, stayed there long enough to reshape chemistry, and then snapped back into a much warmer state. Now, put a civilization onto that world. Global ice does not just kill crops in a few countries, it kills the entire idea of large-scale agriculture as you know it. Most current farming regions would be under glaciers or inside permafrost. Coastal cities and ports would be buried under ice sheets or stranded far from the shrunken, ice-covered oceans. Sea level would be much lower than today, exposing continental shelves, but leaving them frozen and dry, not fertile. River systems would be mostly locked. Seasonal melt pulses would be violent and short. Energy systems would also be in trouble. Hydroelectric power depends on flowing water, which is limited in a deep freeze state. Wind and solar would be affected by changed circulation and heavy snow cover. Fossil fuel extraction, if you even managed to reach deposits, would be far more difficult through miles of ice and frozen ground. Mining for metals would be limited to a few exposed regions, maybe near rift zones or volcanic belts, and shipping those materials would be nearly impossible without liquid ocean lanes. Under global ice, supply chains collapse from both ends. Resources are harder to reach, and routes to move them are cut off. Even if a high-tech species saw the freeze coming, the scale is so large that adaptation would mean concentrating a reduced population into rare ice-free refuges, probably near active rifts or hotspots, and giving up on global infrastructure. Satellites and digital networks do not feed people. You need predictable growing seasons, open water, and accessible minerals to keep a planetary civilization running. In a snowball scenario, you lose all three across most of the surface. From the viewpoint of future geologists, a civilization caught by a Snowball Earth event would leave an odd layered story. Below the glacial deposits, you might find an industrial signal, altered carbon and nitrogen isotopes, radionuclides, plastics, and metal anomalies. Then a thick stack of glacial sediments and dropstone-filled layers records the advance of ice. Above that, cap carbonates and a new set of fossils mark post-freeze recovery, and maybe a different style of life dominating the planet. To someone reading that stack hundreds of millions of years later, the civilization's tech spike would look like a brief, strange chemical line that ends right as glaciation begins. You do not have to reach full snowball conditions to be in serious trouble, though. The same feedbacks and cycles that drive those extreme freezes also operate at smaller scales. Ice and albedo, greenhouse gases, ocean circulation, and cloud feedbacks can produce swings much smaller than a global freeze, but still far beyond what a complex society can easily ride out. Even without total ice cover, you can get rapid shifts in climate zones, rainfall patterns, and sea level that erase coasts and break agriculture. That sets up the next phase of the story, because the real threat for a living civilization is not necessarily a permanent frozen world. It's rapid, hard-to-predict climate whiplash, where things flip from one state to another faster than systems can adjust. History already shows smaller examples of this, with abrupt warming and cooling events that reshaped where people could live and farm. In a high-tech, globally linked world, those kinds of swings become far more dangerous. How stable do you think normal really is if the climate system has a record of flipping faster than forests, crops can keep up? The hard truth is, tipping points aren't theory. They're built into how ice, oceans, and air interact, and they don't need a full extinction event to wreck a civilization. A tipping point is simple in concept: slow pressure, then fast change. You push the system with greenhouse gases, land use, aerosols, or natural cycles. For a while, the response is gradual. Then you cross a threshold and feedbacks take over. Ice melts faster, forests burn more often, ocean currents shift position. The same shove that gave you a small change before suddenly gives you a big one. Paleoclimate records show jumps like this, temperature and rainfall shifting in decades, not in tens of thousands of years. Ecosystems already running near their limits cannot reorganize that quickly. Neither can complex societies that built cities and farms around the last few thousand years of normal. So where do you feel that whiplash first? Almost always in water. Civilizations collapse from water problems before they collapse from abstract temperature numbers. When climate zones move, drought belts can slide north or south by hundreds of miles. Regions that used to get reliable rain find themselves under persistent high pressure. Monsoon systems can weaken, delay, or overshoot, dumping too much rain in the wrong month or almost none in a critical growing season. Freshwater systems, rivers fed by snowpack and glaciers, can first flood as melt speeds up, then crash as ice reserves vanish. Ask yourself what that does to a society built on predictable planting and harvest cycles. Reservoirs run low. Hydro dams produce less power. Cities that thought their water rights were safe discover that the rivers they depend on can no longer hit those numbers. Farmers drill deeper wells, chasing falling groundwater, until that also runs short or gets salty. A few bad years in a row can push rural areas into failure, forcing migration. That pressure moves into cities, which are already stressed by heat waves and infrastructure aging. You do not need an asteroid to break a country. You just need a decade where the rain map shifts and never goes back. While the interior dries or floods in new patterns, the edges of the map move too. Sea level is a very quiet, very ruthless eraser. When average sea level rises even a few feet, about a meter, the practical coastline moves inland. Storm surges right on top of that higher baseline, reaching farther, flooding deeper. Low-lying coastal hubs, deltas and river mouths, the places where you tend to build ports and megacities, become chronic flood zones. At some point, insurance fails, infrastructure rots, and people have to retreat. On the flip side, if currents or ice changes pull water away from certain margins, some ports can end up stranded, with shallower channels or receding shorelines. Either way, the ports your trade system depends on die, and your maps of usable coastline change. In the geological record, that shows up as transgression and regression sequences, layers where marine sediments suddenly shift landward or seaward. Sediment buries old harbor structures, deltas move, and future geologists see only a jumble of sand and mud where you remember a city. Your coastal evidence gets ground up and covered, while new coasts and new deltas grow elsewhere. As temperatures rise and rainfall patterns swing, another system flips with them. Fire. Warmer, drier conditions turn forests and grasslands into fuel waiting for a spark. Fire seasons get longer, lightning strikes in hotter, more unstable air light more areas. Human activity adds more ignition sources. When vegetation dries out, you move from occasional wildfires to regular, large-scale burns. The feedback is ugly. Burned areas can reflect more sunlight at first, but they also release huge amounts of carbon dioxide and soot, and they can change local rainfall by altering how much moisture plants pump into the air. From the rock and ice point of view, those fire regime flips show up as soot and charcoal layers. You can see black bands in lake sediments and in ice cores where fire activity spiked. In a civilization context, that soot might show up alongside industrial aerosols and greenhouse gas changes, marking a time when both climate and land management spiraled. A future scientist reading those layers would see a period where the planet went through repeated, intense burning, not just from natural lightning, but from a landscape and a society that had lost control of fire at scale. Now, connect these pieces back to your world with no spin. You do not need an end-of-life on Earth scenario to lose a technological civilization. You do not need every species gone, every forest dead, every ocean empty. You just need the end of predictability at the scale your systems require. Agriculture cannot afford random multi-year failures across several breadbasket regions at once. Power grids cannot take endless heat waves and storm hits without major upgrades. Trade networks cannot rewire overnight when ports move and sea lanes get more dangerous. In rock terms, a civilization taken down by climate whiplash would leave a signature that looks soft compared to an impact, but still sharp compared to slow background change. You would see a fast rise in greenhouse gases, a linked shift in carbon and nitrogen isotopes, changes in pollen and microfossil assemblages as ecosystems moved or collapsed, a pattern of soot layers from intense fire periods, and marine sediments that record sea level changes in oxygen stress. Above that, you might see a quieter interval, with fewer signs of large-scale industry, as either a reduced society stabilizes at a lower level or a long recovery from near collapse plays out. For you, the harsh line is this: a planet can stay technically habitable while being completely hostile to the kind of high-energy global civilization you're used to. The biosphere can downgrade without going to zero. Life goes on, but not your version of life, with worldwide flights, data centers, container ships, and complex supply chains. The rock record doesn't care whether the last satellite went offline because of heat, flood, or a failed state. It only records that there was a short, intense disturbance in chemistry and climate, followed by something else. So far, every risk has been tied to the planet itself, its interior, its oceans, its ice. But the sky above you is not calm either. There are hazards that don't come from below or from your own emissions. They come from your star and from space beyond, and they hit hardest precisely when you are most dependent on electricity, satellites, and radio. The next layer of the threat is not a slow tipping point, it's a sudden pull of the plug from above, and the rocks may remember that too, in the form of strange isotopes and radiation scars. You live on a planet that runs its entire advanced system on electricity, and the power source that makes that possible, your star, can also knock that system down in one bad burst. Solar storms sound harmless, like a forecast you can ignore, but when a civilization chains everything to grids, satellites, and radio, it's a direct point of failure. Start with solar storms because those are guaranteed, not rare miracles. The sun throws out flares and coronal mass ejections, big clouds of charged particles on a regular basis. Most are small, many miss Earth, but when a big one hits the planet's magnetic field just right, you get a geomagnetic storm. That storm, in turn, induces electric currents in long conductors, like power lines, pipelines, and undersea cables. Those currents are not designed, they're noise, and they can overload transformers, damage equipment, and destabilize entire grids. You are completely dependent on that grid. Power plants, data centers, water systems, hospitals, fuel pumps, and communication networks all assume a stable electric supply. Satellites that give you GPS, weather data, internet links, and communication for aircraft sit directly in the path of energetic particles. In a major storm, satellite electronics can be damaged, or their orbits can be altered by changes in the upper atmosphere. Navigation signals can become unreliable or disappear for hours to days. For a modern society, even a temporary hit is serious because so many systems are linked and because spare transformers and satellite replacements are slow to deploy. Now look at higher energy events that do not just hit hardware, they leave a chemical mark. Cosmic rays and bursts of high-energy particles from solar events or distant explosions can interact with atoms in the atmosphere, creating rare isotopes, such as certain forms of carbon, beryllium, or chlorine. These isotopes then get locked into ice, tree rings, or sediments. When scientists drill ice cores and measure these, they see spikes at particular times, short periods when radiation from space was stronger than usual. Those spikes are the "this came from space" signature. They tell you that, at specific points in the past, Earth's upper atmosphere was hit harder than normal. In recent history, we have smaller examples, but over longer periods, you can have larger unknown events. The rock and ice record does not always tell you exactly what the source was, but it does tell you that the planet is not shielded from high-energy surprises. From a civilization standpoint, these events might not kill you directly, but they can ruin electronics, stress the ozone layer, and increase mutation rates in ways that matter over time. Ozone is another weak point. The ozone layer in the stratosphere absorbs most of the sun's harmful ultraviolet radiation. High-energy events like strong solar proton storms or nearby cosmic explosions can trigger chemical reactions that break down ozone. If you thin that layer enough, more UV reaches the surface. That means more damage to plant tissues, more skin cancer risk for animals, and more stress on crops that evolved under a certain UV level. Agriculture is sensitive to temperature and water, but it is also sensitive to radiation. You do not want growing seasons under a harsher UV load when you are already juggling climate stress. Combine that with what you already know. Earth does get hit by big stuff. Impacts like Chicxulub are rare on human timescales, but over hundreds of millions of years, they are statistically certain. Even smaller objects, maybe tens to hundreds of yards or tens to hundreds of meters across, can destroy a city or region if they hit in the wrong place. Near misses already happen. We sometimes catch them with surveys, sometimes we identify them after the fact. Solar superstorms like the 1859 Carrington event have happened, and similar or stronger events will happen again. The difference now is not the hazard, it is what that hazard can break. This is the part that matters for your position in time. Your tech can make you more vulnerable than pre-industrial societies, not less. A medieval village hit by a strong solar storm would have seen strange lights in the sky, maybe a compass needle behave oddly. Then it would have continued with its day. A modern city hit by the same level of storm can lose power, communication, navigation, and financial systems. Our networks are tightly coupled and globally synchronized, so a failure in one region can propagate, like a cascade, through markets and supply chains. If a major solar storm hits while grids are heavily loaded, transformers can burn out on a large scale. Building new large transformers can take months or years, especially if the factories that make them are also damaged or without power. A long outage isn't just an inconvenience. It means food spoils in storage, fuel cannot be pumped easily, digital payment systems fail, and hospitals and water systems have to run on limited backup. A civilization like ours has never experienced a Bond event or Carrington-level storm with today's level of dependency. The test hasn't happened yet, but physics says it will. From a geological and chemical point of view, a tech-heavy civilization hit by strong space weather can leave two overlapping signatures. One is the direct space signature, isotope anomalies in ice and sediments from radiation bursts. The other is the tech signature you're already familiar with, shifts in carbon, nitrogen, and synthetic compounds from industrial activity. If a strong solar or cosmic event triggered grid collapses, infrastructure fires, and industrial accidents, those might show up as linked peaks in soot or particular pollutants. A future analyst could see that at some moment, something from space and something from industry hit the planet at the same time. There's a deeper implication hiding in all this. The more advanced and electrically connected a civilization becomes, the more its basic functions depend on a calm magnetosphere and stable space weather. Mining, manufacturing, food distribution, medicine, transport all depend on systems that can be disrupted from above with almost no warning. Pre-industrial societies took their biggest hits from floods, droughts, and war. An advanced one adds geomagnetic storms, radiation spikes, and orbital debris cascades to its list of failure modes. For a species trying to understand whether it's alone in the universe, this also changes how you think about the silence. A civilization might get far enough to build satellites and big grids, then take a major hit from its star or from a nearby cosmic explosion, and drop back down without vanishing entirely. In the rock and ice record, you would see a brief period of intense techsignatures, then a reduction, maybe with a radiation spike in the same layers. To outside observers, the planet might still look habitable, but the advanced phase would be finished or degraded, leaving only subtle traces. You can respond to this in two main ways. One is to harden your systems, build better shielding, make grids more resilient, store more power, and keep critical functions safe from geomagnetic currents and particle storms. The other is to push some of your infrastructure and records off the planet, into locations where they are not constantly being recycled and eroded. That second option matters for detection, because if Earth melts, scrapes, and buries most of its own history, the cleanest place to look for a technological layer, yours or anyone else's, might not be on Earth at all. Which raises the next question: if you wanted to find solid proof that a civilization ever existed here or on any world like this, where would you actually search? What places keep their records without constant tectonic and weather destruction? And what kind of artifacts or chemical signals would stand out there, long after the home planet has reset itself? So if Earth is this good at erasing its own history, where do you actually store proof that a civilization ever existed? Where do you put evidence so the planet can't just chew it up and recycle it? The obvious answer is uncomfortable. The safest archive of our existence might not be on Earth at all. Start with the moon, because it is the closest thing to a natural hard drive you have. The moon does not have plate tectonics. It does not have rain, rivers, or oceans, and it does not have an atmosphere thick enough to drive weather. Its crust does not get pushed around, melted, and rebuilt the way Earth's does. Impact craters from billions of years ago are still visible. Layers of ejecta from big hits are still roughly where they landed. The surface slowly grinds into dust from micrometeorites, but it does not get erased and recycled into new crust. That means impact layers and surface deposits can stay put for timescales that make Earth look short-term. If you leave a metal object, or a glass panel, or a piece of machinery on the moon, it will not rust in air or get buried by rivers. It will sit there under raw sunlight, temperature swings, and tiny impacts. Over millions of years, it will degrade, it will break, it will slowly get mixed into the upper soil, but fragments can survive far longer than anything left on an active, wet world. From a detection point of view, the moon is where you go when you want surface evidence that can outlive continents. So here is the sharp question. If some earlier civilization reached space, even briefly, where would their hardest artifacts be now? On their home planet or on their moon? Earth can bury a launch pad under sediment and cities. The moon will quietly keep landers, crashed probes, and debris close to the surface. Even if hardware is smashed into pieces, you would still find unnatural alloys, precision machined shapes, or glass compositions that planetary geology does not normally make. You do not need a perfect flag or an intact base. You just need enough strange material that, under a microscope and in a mass spectrometer, screams engineered. But what if Earth totally wipes its own direct record? What else should you look for beyond obvious landers? Think in terms of spillover. Every launch throws exhaust and microscopic debris into high-altitude paths. Some particles escape into interplanetary space. Some collide with the moon over long timescales. Industrial activity also releases rare gases and isotopes that can leak into space, get picked up by solar wind, and implanted in lunar dust. If a civilization ran high-energy industry for a long time or did a lot of nuclear work, trace amounts of their byproducts could be embedded in the moon's surface as unusual isotopic ratios in the top layers of regolith. So if Earth has lost chapters in its own crust, it makes sense to treat the moon as a backup copy of parts of those chapters. You would drill cores of lunar soil, layer by layer, and measure noble gas isotopes, metal patterns, and strange compounds, looking for a narrow horizon where the chemistry goes off script in a way that does not match normal solar and cosmic processes. That is a search for civilization residue that Earth's erosion cannot undo. Then there's Mars, which plays a different role, a comparator and another archive. Mars is smaller, colder, and much drier than Earth. It lost most of its atmosphere long ago. It does not have active plate tectonics in the way Earth's does. Large regions of its surface are ancient, scarred by craters and old river valleys. Wind erosion reshapes the top layer. Dust storms move fine material around, but entire crustal blocks are not constantly recycled into the mantle. Why does that matter? Because Mars preserves extremely old surfaces and sedimentary layers that still sit near the top. Old lake beds, dry deltas, and sediment piles could hold a very long history of climate and chemistry, frozen and buried, but not melted and reused. If Mars never had a technological civilization, it is still useful because it shows what a long-term, non-industrial planet looks like in chemical and mineral detail. If Mars did host one, either native or visiting, its record would be less scrambled than Earth's. Artifacts could be buried by dust rather than ground up by tectonics. So if you were serious about testing for past industry in the solar system, you would not only drill Earth's deep sea cores, you would also drill Martian sediments, collect core samples from old lake beds, and scan for strange isotopes, synthetic polymers, unusual metal distributions, and any materials that look out of place in known Mars geology. Mars gives you a second dataset, a way to say, this is what a planet with no industry looks like over billions of years, and then compare that to Earth and the Moon. There is another obvious sign of a spacefaring phase, and you are already making it right now: orbital clutter. Satellites, spent rocket stages, fragments from collisions, all of that forms debris belts around Earth. In low Earth orbit, drag from the thin atmosphere brings objects down in years to centuries. In higher orbits, debris can last much longer, thousands or even millions of years for some paths. Around other worlds or in deep space at stable points like Lagrange positions, certain orbits can stay stable on huge timescales. So here's a question. If a previous civilization used orbits heavily, where would you expect their leftovers to be now? Close in, most would have decayed and burnt up in the atmosphere. Farther out, especially in high orbits or around moons and small bodies, you might still find clusters of artificial objects, heavily eroded but present, or unnatural material deposited by decayed orbits and impacts. You might detect that indirectly first, as odd radar reflections, non-natural density and reflectivity statistics for small objects, or as tiny fragments of advanced alloys in micrometeorite populations hitting the Moon or Mars. From a long-term perspective, orbital clutter and lunar artifacts are more durable than surface cities. They avoid the worst of tectonics and weather, even if they face radiation, micrometeorites, and slow degradation. If a civilization makes it to space at all, it paints a faint but detectable third layer of evidence across its system, on top of atmospheric chemistry and rock chemistry. And that layer can outlive the home planet's surface record. Now step back and look at the civilization angle with no sugarcoating. Earth is too active, too wet, too alive in a geologic sense to keep neat, readable records of everything that happens on it. That's good for life, bad for history. The best proof of past industry, ours or anyone else's, may not be buried under some continent. It may be sitting in quieter, simpler places, like the lunar regolith, Martian sediments, or stable orbits where nature does not constantly rearrange the furniture. For us, that cuts both ways. If we want to be detectable to anyone who comes after, and if we want a backup of our own story that survives our worst mistakes, we should expect Earth to fail us long term. The safest archives are off-world, on surfaces that do not move, in orbits that decay slowly, and in materials that are hard to confuse with natural rock. For a scientist in the far future, or an alien looking in, the combination of strange layers on Earth, plus hard artifacts on the Moon or Mars, plus weird orbital debris patterns would be a strong, multi-channel confirmation that a spacefaring phase really happened here. So if that is where the best evidence might be, how would you actually design a serious test, right now, to look for a pre-human tech spike? Not with myths or guesses, but with cores, drills, detectors, and a plan that can say yes or no with real confidence. If you really wanted to know whether Earth had an industrial civilization before humans, how would you actually test it in a way that could prove you wrong, not just confirm your favorite theory? You would need a plan that doesn't rely on myths, lost continents, or lucky fossil cities. You would need something you could hand to a skeptical scientist and say, if it happened, this is how we would see it. And if we do not see it, here's what that means. Step one is where you look, because most places on Earth are terrible archives. You go for deep sea cores and quiet basins, spots where sediment has been raining down steadily for tens of millions of years without major breaks. These are usually in the deeper parts of the oceans, far from steep continental margins, or in long-lived lake basins where mud builds up layer by layer. You send drilling ships out, you punch through hundreds, sometimes thousands of feet of layered sediment, and you pull up cores that are essentially time columns, with the oldest material at the bottom and the youngest at the top. In those quiet basins, the goal is continuity. You want as few gaps as possible. No big inconformities, no massive slumps, just a slow, predictable accumulation of tiny particles, shells, dust, and organic material. That's where thin global signals, things like a brief pulse of pollution or a fast carbon shift, stand a chance of being recorded as a distinct layer, maybe only a fraction of an inch, a few millimeters thick, but real. You would especially target time windows that are poorly preserved on land, intervals where continental rocks have been eroded or metamorphosed, because the deep sea might still remember what the continents forgot. Once you have those cores laid out in the lab, sliced and labeled, the next question is obvious. What exactly do you measure? What data actually tell you this looks like industry instead of just another natural spike? That is where isotope forensics comes in. You would analyze carbon isotopes, looking for sudden shifts toward lighter carbon that could mark rapid release of fossil carbon. You would measure nitrogen isotopes, hunting for patterns that fit huge amounts of industrial fertilizer, changing how nitrogen cycles through land and sea. You would check sulfur isotopes, because big industrial processes and extreme anoxia can leave distinctive sulfur signatures. You would also look for long-lived radionuclides and their decay products, combinations that do not match natural reactor zones or background uranium and thorium decay. The key is not one number, it is combinations. Nature can cause a carbon isotope excursion, for example through a massive volcanic event or a big methane release, but it will have a certain shape and timing, and it will usually come with specific sulfur and metal patterns. Industrial activity will likely show a different pattern, a short, sharp carbon change paired with nitrogen shifts that match artificial fixation, plus radionuclide ratios that point to reactor-grade or weapon-grade processing. So you treat the sediment like a crime scene, and isotopes are your fingerprints. But even if the isotopes look strange, you want more than chemistry. You want hard, physical stuff, something you can hold up and say, this does not belong in a purely natural layer. So the next step is to look for a triad: soot, metals, and polymers, all packed into the same narrow horizon. You scan the sediments for black carbon, tiny soot particles that form from intense, widespread burning. You check whether the soot level spikes suddenly and whether the particles look more like combustion from many diffuse sources, not just one local wildfire or a single large eruption. At the same depths, you search for unusual metal distributions, like elevated concentrations of copper, lead, rare earth elements, or alloy patterns that do not match normal erosion products or volcanic ash. And you search for synthetic polymers, microplastic-like fragments, and strange carbon-rich particles that resist breakdown and have chemical bonds not normally produced by biology or simple geochemistry. Finding any one of those things might be explainable. Nature can make soot. Volcanism can concentrate certain metals. Some organic molecules are tough and weird even without industry. But if you find all three, a soot spike, a metal anomaly, and synthetic-looking polymers stacked tightly together at the same depth across multiple cores, that is very hard to write off as a purely natural accident. That is your industrial triad, a physical package that says, in this thin slice of time, someone was burning, mining, and manufacturing at serious scale. Of course, there's a trap here. A single weird core can just be local contamination, a landslide, or some strange basin history. So you have to ask, how do you turn this one site is odd into this was a global event, the whole planet felt this at once? You do that with synchronization. You date the cores as precisely as you can using multiple methods. You link volcanic ash layers to known eruptions. You use microfossils and their known ranges to set relative ages. You use magnetic reversals recorded in the sediments, where the orientation of tiny magnetic grains flips as Earth's field reverses, to line up different cores on the same timeline. You apply radiometric dating where possible, using decay of certain isotopes in volcanic material. Then you ask a hard question. Does the same kind of industrial triad or the same kind of isotope anomaly show up in multiple basins, on different sides of the world within the same narrow time window? If the answer is no, if the anomalies do not line up in time and space, then you're probably looking at local oddities, interesting geology but not a civilization. If the answer is yes, if you can show that a strange carbon and nitrogen signal, plus a spike in black carbon, plus unusual metals and polymers, all appear at roughly the same age in Atlantic cores, Pacific cores, Indian Ocean cores, and maybe in lake sediments on land, then you have something else. You have a global, synchronized spike, like a thin scar around the planet. At that point, you compare it to all the natural candidates you already know: large igneous provinces, asteroid impacts, known mass extinctions, big ocean anoxia events, and you see if any of them fit the pattern. If none do, if the only way to explain the combo of isotopes, soot, metals, and polymers is large-scale industry, then you have a serious case for a pre-human tech phase. You still argue about details, you still refine the dates, but the core claim would be testable and repeatable. So what happens if you actually run this test? If over decades you pull cores, scan isotopes, look for plastics and metals, and you find nothing that looks like an industrial triad in deep time, nothing that cannot be explained as volcanic, impact-driven, or biologically driven? Then you have learned something too. You haven't proven that a civilization never existed because Earth's record has gaps and erases surfaces, but you have set an upper limit. You can say with some confidence that no past civilization pushed the planet's chemistry as hard and as globally as we are pushing it now, at least in the intervals you can still read. And that is where the final escalation really hits. Earth has multiple proven reset buttons. Big impacts, supervolcanoes, ocean anoxia, snowball glaciations, abrupt climate shifts, space weather shocks, and slow, grinding tectonics that recycle the surface. On top of that, the only durable signatures of a tech phase are global chemical scars and off-world artifacts. Our own layer, the one we think is so massive and important, is thin, maybe a few inches, a few centimeters in future rock, wrapped inside a planet that is perfectly capable of wiping it out or burying it under something much more violent. The universe may look empty not because civilizations never arise, but because their active phases are short, their physical traces are subtle, and their planets are good at cleaning up. When you run the numbers, our entire industrial age is barely a blip on geologic time. The data we leave in rocks and on the moon will be thin and easy to miss. The terrifying part is not just that we might not find anyone else. It is that even if others came before, on this world or on others, their chapters might already be gone, erased by the same processes that are quietly lining up against us now. So when you zoom out, the question stops being, is the universe empty, and becomes, how long does any civilization get before its own planet, or its own star, or its own choices reset the board? On Earth, with everything you have just walked through, that window looks narrow, and your layer, the one you're living in right now, looks very, very thin. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.